Once the system's structure and cooling are guaranteed, the next critical step is to properly manage cell aging and degradation. In utility-scale systems, even a 2% capacity loss can result in thousands of euros per year in penalties or lower PPA revenue. The most common degradation mechanisms in lithium-ion batteries include capacity loss, between 2% and 3% per year at 20 degrees Celsius, and can reach up to 8% at 40 degrees Celsius. SEI growth of the solid electrolyte interface layer. This is the main cause of degradation in LFP batteries. Microfractures, critical at temperatures above 2 degrees Celsius, especially in NMC chemistries. Modeling. Semi-empirical approaches, such as the P2D model or circuit equivalents, are used for thermal and electrical simulations. Failure to understand and model these mechanisms leads to sizing errors and operating cost overruns. As shown in the graph on the right, temperature exponentially accelerates degradation. Therefore, active control strategies are applied. Optimal operating window between 18 and 25 degrees, with a maximum variation of plus or minus 0.8 degrees. Mandatory pre-cooling if charging rates exceed 1.5 C. Thermal contingency. Charging is actively limited if internal temperatures exceed 35 degrees Celsius. Applying this proactive thermal control extends service life by 20% and reduces OPEX by up to minus 15%. One of the best ways to anticipate failures is to monitor internal resistance using techniques: impedance spectroscopy, EIS, current pulses, frequency analysis. Detection, anomalies greater than 7% compared to the reference group. Correlation. Every increase of 25% in impedance implies approximately minus 15% loss of useful capacity. Recommended frequency. Perform full diagnostics every 50 cycles for predictive monitoring. This technique allows for early warnings to be generated before irreversible degradation occurs. Therefore, charging and discharging are not enough. The way we do it directly impacts the system's LCOE. Standard charging, pink bar. This is the least cost-efficient. Limited DOD, between 10 and 90%. Extends service life by 2.3 times compared to using 100% SOC. Multi-stage charging, CCCVCC. Reduces stress. Asymmetric charging. Discharge at 1 C and slower charge at 0.7 C. Extended CV. More than 30 minutes at constant voltage to reduce mechanical stress. Smart combined charging. Reduces the LCOE to minus 18% by optimizing cycles. With this data, we see that lifecycle management is not a laboratory issue, but a decisive factor in the profitability and reliability of BESS systems. One of the most critical and often underestimated aspects of BESS plants is technical fault management and operational safety. Here, we address both prevention and response to thermal, electrical, mechanical, and cyber incidents. The safety hierarchy in a BESS system is divided into different levels. Thermal faults, thermal runaway, a chain reaction between cells. Trips due to overtemperature and cooling sensor failure. Electrical faults, internal short circuits. Overcurrents due to control errors. Faulty contactors. Mechanical faults, structural fractures. Electrolyte leaks. Corroded or improperly installed connectors. Cyber faults, firmware failures. BMS or SCADA communications problems. Thermal failure remains the most common cause, but firmware and control system errors are increasing due to the complexity of new BSs. To prevent a failure from becoming a serious incident, multiple barriers must be activated. Detection: VOC, hydrogen, smoke, and heat sensors. Alert: visible local alarm plus remote alarm to SCADA or control center. Suppression: aerosol, water mist, or inert gas systems. Isolation: physical containment of gases and heat to prevent spread. These protocols must be validated every 6 months and be part of the FAT SAT plan prior to commissioning. When a serious failure occurs, it is essential to understand what caused it. Advanced forensic techniques are used. Computed tomography non-invasively identifies internal fractures. Gas chromatography detects combustion or degradation byproducts. Black box. Retrieval of data from the last minute at 200 Hz, BMS logs. SEM microscopy. Analyzes electrodes, separators, and SEI formation. These diagnostics help adjust predictive models and improve future generations of batteries. 100% of BESS systems must undergo FAT, Factory Acceptance Test, and SAT, Site Acceptance Test. The most relevant tests may include dielectric and actual versus nominal capacity testing. Round-trip, efficiency. Response to grid failures, and black starts. Cell balancing. Leak detection and sensor calibration. BMS communications validation. Failing to perform complete FAT SAT testing exponentially increases the risk of catastrophic incidents in the field. In short, security in BESS systems is not just a regulatory requirement. It is a technical and operational requirement that impacts availability, reputation, and ROI. In large-scale BESS systems, control is not local. It is multi-level, distributed, and requires a perfectly synchronized communication architecture. Without good coordination between the EMS, PPC, BMS, and SCADA systems, the system simply will not operate stably or safely. This diagram shows the four major control components in a hybrid system: EMS, Energy Management System, responsible for overall energy dispatch and coordination with the TSO/DSO. PPC, Power Plant Controller, regulates the active-reactive set point and coordinates inverters. BMS, Battery Management System, controls the safety, balancing, and SOC/SOH of each module. SCADA allows visualization, history, and supervised control from a control center. The most common conflicts can be signal precedence between EMS and BMS. Timestamp problems, desynchronization, conflicting set points. The solution would be to clearly prioritize the order flow between the EMS, PPC, and BMS and use protocols with secure handshaking. Proper SCADA integration is essential for auditing, remote diagnostics, and cybersecurity. The selected protocols must ensure compatibility, low latency, and cybersecurity, IEC 61850, ideal for electrical substations. It allows for standardized, interoperable models and high-security. Modbus TCP, easy to implement, widely used in inverters. OPCUA, object-oriented, encrypted, platform-agnostic. The most comprehensive for modern SCADA. In new projects, it is recommended to use OPCUA for the plant level and IEC 61850 for integration with substations. The control logic in a BS system is structured into three levels. Plant level generates set points based on market prices, demand curves, or network services. PQ, ramp control. Inverter PCS level implements PQ regulation, LVRT, VF modes, and ramp control, PF. Module level, the BMS manages balancing, protections, and internal safety. This structure allows coordination from the electrical grid to the individual cell, ensuring safety and dynamic stability. The graph shows the required latency by type of function. Electrical protections. Response less than 20 milliseconds. Primary regulation. Less than 100 milliseconds. Auxiliary services. Reporting, arbitration. Less than 1 second is acceptable. Some key recommendations include GPS PTP synchronization. To ensure consistent timestamping in rapid events. Predictive control. Using distributed MPC control with a time horizon of between 5 and 15 seconds. Local cache. Controllers must be able to operate during temporary communication failures. In plants larger than 50 megawatts. This system is essential to comply with grid codes and avoid penalties. As we can see, synchronization and control architecture are not only necessary for efficiency, but also for the safety, traceability, and flexibility of the hybrid system. A large-scale BESS installation cannot go into operation without rigorous validation. This testing phase is critical to ensure that the system meets functional, regulatory, and safety requirements under real-world conditions. The two types of testing for BESS system validation are FAT, Factory Acceptance Test, performed in the factory. It is a controlled environment. Tests from 1 to 3 days. Module by module are tested. Medium criticality. detects manufacturing defects. SAT, site acceptance test, tests in real-world conditions, already in the plant. Full integration with SCADA, grid, and inverters. Can last from 1 to 4 weeks. The entire system is tested. High criticality. It is the final filter before operation. Many thermal and electrical failures occur due to poorly executed or incomplete SATs. Load and dynamic response testing allows you to analyze the behavior of the BIOS system under varying loads in real time. Capacity: C5, C2, 1C. Round-trip efficiency must exceed 89 to 90%. Ramps: 0 between Pmax and Pmax between 0. Thermal rise. Monitoring of thermal variation during unloading. The typical duration is between 8 and 24 hours per rack. Thermal analysis: IR thermal imaging. Distributed sensors. P&O and step response testing. This test ensures that the system can respond to TSO loads without overheating or critical delays. Simulating grid faults allows verification that the system complies with the grid codes required by the system operator. Black start: autonomous restart of the system from 0, island mode. Ride through: tolerance to voltage dips, LVRT, HVRT. Surge: protection against transient events. Anti-islanding: detection and reaction to unplanned disconnection. The applicable standards are EIEC 62930-321 IEE 1 547 2018. The necessary equipment is grid simulators. DIP generators. PQ analyzers. These tests are essential for accessing the ancillary services market or signing a PPA with demanding technical conditions. Now we compare the actual performance with that predicted by the digital twin or the simulation model. Pass if it is within plus or minus 2%. Warning: if there are deviations of up to 5%. Fail if the deviation exceeds 5%. Typical tools include MATLAB models, Python. Digital twin with real feedback. Benchmarks with SCADA plus thermal sensors. This validation is the link between theoretical engineering and actual operation. If it fails here, the project is not financially viable. We quote VE seen how to validate all critical system parameters in the field. But what if we could anticipate failure before it occurs? We'll see that in the next video.